In Boston, a deadly flaw brings traffic to a screeching halt.
That epoxy gave out and the concrete fell down.
A river crossing collapses in Wales, devastating the local community.
So I picked the phone up. She said, the bridge has come down. Well, it's just unbelievable.
In Milwaukee, a bridge begins crumbling in broad daylight.
The fear was that the entire structure might come tumbling down.
And a dam collapse in Spain changes the course of history for one town. With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. When engineers go big, every last detail must be checked and double-checked. Because the most innovative builds can be undone by the smallest oversight. Like this interstate tragedy in the capital of Massachusetts.
This was a structural project on a supersized scale.
A massive infrastructure upgrade to a city's road network.
At its peak, the project was employing upwards of 5,000 people.
A disaster that revealed a weakness hidden within the system.
There was a lot of talk about whether this was a safe project.
Boston, Massachusetts, was founded nearly 400 years ago beside the Charles River and has grown to become one of America's most visionary cities. Tim Logan is a local journalist.
Boston is one of the oldest and most historical cities in the United States. The beginning of the Revolutionary War was here, and it's always been an innovative city. It prides itself on that.
Boston is home to the Red Sox, the Revolution, and radical thinking. So when it comes to testing boundaries, this city doesn't hold back.
However, in terms of urban infrastructure, Boston was stuck in the past.
With a street plan devised in the days of horse and cart, for decades, Boston was one of the most congested cities in America.
This was a clear obstacle to progress, as transportation reporter Tom Palmer explains.
A lot of the streets and paths in Boston that are still here today were basically formed by cows walking around, and they're narrow. After World War II, Boston, like many American cities, was a crumbling city. People didn't want to come here, nothing was being built.
At the center of Boston's urban decline stood a particularly troublesome freeway. Although it wasn't very old, it came to symbolize a city unwilling to change.
This stretch of highway was built in the 1950s, and it was hopelessly out of date. The elevated freeway, which had been built as a solution, had effectively cut the city in half.
It divided the city from its waterfront.
Boston was gridlocked. Entire neighborhoods were cut off, and the elevated freeway was in serious decline.
It was never designed to cope with the huge amount of traffic. This city was going nowhere fast.
It was stall and crawl all the way through town at rush hour and sometimes all day long. 90,000 cars is what it was designed for. 180,000 cars was what it was taking toward the end, and it was crumbling and needed to be replaced.
In 1991, work began on an engineering project that aimed to catapult Boston's transportation infrastructure into the future. It was called the Big Dig.
To open up the city and reconnect communities, the bold decision was taken to go under the very heart of downtown.
In the early 90s, a construction project began, the Big Dig, to replace the old elevated central artery and to put it underground, right in the middle of the city.
The project would reroute the section of I-93 that runs through the heart of the city. It would include a new tunnel and a new bridge, complete with additional green spaces in the center of Boston.
This was one of the most ambitious engineering projects ever undertaken. 6 huge sections of highway, tunnels running 1.5 miles or 2.5 kilometers right under the heart of downtown, and on top of that, the widest cable-stayed bridge in the world.
The idea was to get the cars out of sight, out of mind, and to put something really good on the surface, and that's the park.
They were going to turn a once desolate space into a beautiful park and reconnect the city with the river and the people with each other.
The scale of the dig was enormous, and it wasn't going to be easy.
The biggest challenge for engineers was that throughout the entire construction, they had to keep the city moving, however slowly. So the tunnels needed to be built under the city while the old elevated freeway remained open.
Engineer David Beck worked on the project.
It was always a high priority to keep the existing traffic flowing as smoothly as possible while maintaining progress on the construction.
And if that wasn't enough, it all had to be done in unstable conditions because most of Boston was built on reclaimed land dating back over 200 years.
Digging on a scale like this, directly underneath a bustling city and through precarious reclaimed land, presented engineers with a huge challenge. And the city with a hefty price tag.
This was the most expensive highway project in US history. It went 14 years and more than $12 billion over budget.
But an ever-increasing schedule and spiraling costs weren't the only issues with this project. In 2006, after all of the main bridges and thoroughfares had been opened to the public, tragedy struck.
There was a 3-ton piece of concrete used for ventilation that fell and killed a lady, unfortunately.
A project that had initially brought hope to the city sent a shockwave through Boston.
There was a lot of fear about driving in any of the tunnels. There was a lot of talk about whether this was a safe project, whether it had been done safely.
After the collapse, there were real concerns about the overall safety of the entire project.
In the wake of the disaster, a federal investigation was launched to uncover what had caused the collapse. The answer lay in a material used in the construction called epoxy.
Epoxy is a structural adhesive which is widely used in the construction of everything from aircraft to automobiles, anything where a high-strength bond is needed.
The tunnel design included an overhead ventilation system suspended from the ceiling, but one 90-meter section of the tunnel lacked the necessary support structure, so a retrofit solution was needed. Holes were drilled overhead and long anchor bolts inserted, secured with epoxy for extra strength.
The investigation concluded it had something to do with the epoxy that those heavy panels were hung in and the bolts that went into them.
The concrete roof had been poured before they designed the ventilation system. And in that area of 300 feet, they had to go ahead and drill in inserts, and they used grouted, epoxy grouted inserts into it rather than mechanical sections. And that, over time, that epoxy gave out and the concrete fell down.
The investigation also revealed that the epoxy-secured anchor bolts used in this section were incorrectly installed. Not only that, but this retrofitted solution was an inadequate choice for the ventilation system that weighed hundreds of tons. Concrete expert Gary J. Klein was part of the investigation.
We're going to test the pullout strength of an anchor that's of the same size as the anchors that was used in the connector tunnels for the Big Dig and is embedded the same distance into the concrete.
This test shows the load-bearing capacity of anchor bolts that have been properly installed. The concrete has been drilled and cleaned, and the epoxy correctly applied.
This pump is pumping the hydraulic ram, which is extending this larger rod, which pulls out, if you will, the smaller rod that's embedded into the concrete. the concrete failed, as expected, in what we call a breakout failure. So the epoxy held, but the concrete itself was only so strong, and we got a breakout failure.
In this instance, the concrete itself failed before the epoxy anchor bolt joint. In this second test, the anchor bolts have been installed incorrectly, similar to what happened during the Big Dig. The results are clearly different.
So these test results are quite different than compared to the first test. And the first thing you'll notice is that the epoxy is failing. The rod is literally pulling out of the concrete without damaging the concrete itself. In the first test, where the epoxy was properly installed, it was strong enough to force the concrete to break out. In this case, it's nowhere near strong enough.
The correctly installed anchor bolts are more than 4 times as strong as those installed incorrectly.
The failure mode was the same type of failure that occurred at the Big Dig. It slowly pulled out without having enough strength to cause a breakout failure of the concrete or a failure of the rod itself.
But what could engineers do to solve this problem and salvage the entire Big Dig project for the city of Boston? After the deadly tunnel collapse of 2006, all of the incorrectly installed anchor bolts used in the ventilation system were closely examined. 242 were highlighted as potentially dangerous. As a fix, a new type of anchor bolt was proposed. Concrete expert Gary Klein explains.
They insert this entire assembly into the hole, but then there's a second step in which they rotate the outer portion of the assembly such that these flanges are forced to spread out around the bottom, such that these flanges give direct mechanical attachment, if you will, between the anchor and the concrete. They should provide excellent performance for the lifetime of these tunnels. You would not expect to see any kind of pull-out over time.
All the anchor bolts had to be replaced with these new, stronger, expanding versions. After the upgrades, Boston's tunnel ventilation was deemed safe again for commuters.
Despite its problems, the escalating costs, and the massive overruns, the Big Dig definitely worked.
The Big Dig was an engineering marvel in many ways. Most people recognize that Boston would not be the booming city it is today if it didn't have this highway put out of sight, out of mind underground, and a really nice park on the surface.
Running the freeway underground has given the city and its people a chance to reconnect.
While this project at times nearly fell apart, it ended up putting the city of Boston back together again.
When it comes to massive engineering projects, double-checking even the smallest detail is crucial. Getting it wrong can result in devastation. Like this engineering disaster in Wales, where a tiny miscalculation led to a catastrophic failure.
An error in the design drawings brought down a 5,000-ton structure.
A tragedy that shocked an entire community.
The whole bridge line at 45-degree angle straight across the road. Well, it's just unbelievable, you know.
And a deadly disaster that forced an immediate change in the way bridges were built.
Lessons were learned so that hopefully this type of disaster will never happen again.
In southwest Wales lies the quiet port town of Pembroke Dock. Soaring above the town is the imposing Clevi Bridge. It spans more than 800 meters and connects this peninsula to the rest of the country. But it wasn't always so easy to cross this divide, as retired police officer Phil Lloyd explains.
We couldn't have a better place to live. You've got this glorious waterway which stretches 10 miles down to the open sea and 10 miles further up to the county town. There's only 2 ways to cross the river in the years gone by. You either went by ferry boat, and if you missed the ferry boat, then you had a 28-mile trip right around the main road.
Once a vital Royal Navy dockyard, in the 1960s the military shipped out, and the townsfolk had to look across the water for work.
The ferry could only carry 24 vehicles and around 250 pedestrians per crossing. The construction of a large oil refinery in Milford Haven in the 1960s on the north side of the estuary meant a more practical solution was needed to connect these parts of the country.
So back in the late part of the 60s, it was proposed that a high-level bridge should be built. It was a godsend, really, for the majority of people because, you know, you never had to take this long journey again or go on the ferry boat, especially in rough weather.
Construction of the Clevi Bridge began in 1969 and was due for completion in 1971, taking a very direct route.
On the southern end, the bridge would cut right through the heart of the village, going between houses and across gardens.
Construction took place simultaneously on both sides of the river and was made up of 7 spans built in self-contained sections that would then be moved or trundled along the partially completed bridge and lowered into place in what's known as a box girder design. This is a tried and tested technique that's both time and cost efficient, as engineer Brendan Walker explains.
This is a cross-section through a box girder bridge. Now, you could build a road by creating lots of layers of solid material all the way through, but engineers realised that a lot of this material in the centre is pretty much unused. So you're using a fraction of the materials, it's very light, and particularly in long-span bridges where you've got wind whipping over the road surface, it's actually a pretty efficient aerodynamic shape.
Box girder bridges have been around since the 1800s. They're a relatively simple but very effective way to build a very strong and sturdy structure. At least that's the theory.
To give the bridge added strength and support to the piers, the design called for using 3/4 inch or 1.9 centimetre thick steel diaphragms.
What these diaphragms do essentially, they sit on top of these piers and they transmit all the force of the traffic directly through the diaphragm and into the piers below. So they do an incredible, important job inside the bridge.
On a warm summer's day in 1970, local residents were going about their business as the Clevi Bridge was being constructed directly above their heads. Former police officer Phil Lloyd was on his way to work.
On June the 2nd, Tuesday, June the 2nd, 1970, it was extremely hot, one of the hottest days we'd had for years. I went into work into Pembroke Dock, which is just over the hill there. And I went into work at 2 o'clock. And I'd only been in work about 20 minutes when the switchboard operator said, "Your mother-in-law's on the phone." So I picked the phone up. She said, "The bridge has come down." Now, mother-in-laws do tend to exaggerate a bit, and I thought that's what she was doing.
But Phil's mother-in-law was stating the facts. At 2:16 p.m., as the 75-metre second section of the southern end was being lifted into place, disaster struck. The entire span buckled and came crashing down through the middle of town. Phil Lloyd was first on the scene.
So myself and my sergeant, Bryn Phillips, we jumped in the van and we came down this road. It comes all the way down here, which leads into the village. And if you can imagine, you come here to find that structure at a 45-degree angle going across the road, which, well, it's just unbelievable, you know. And of course, everybody is out of their houses wondering what is going on.
Despite tons of steel and concrete falling more than 30 metres onto the town, amazingly, it missed both houses and residents. But those working on the bridge weren't so lucky. 5 construction workers were injured, and tragically 4 lost their lives in the disaster.
It was only the fact that they had been careful to avoid building directly over the top of houses that prevented this disaster from being a whole lot worse.
People wanted to know, you know, what had happened, why had it happened.
The construction site was immediately shut down and questions were already being asked. How had a seemingly simple box girder failed so catastrophically? An investigation into the Clevi Bridge collapse was immediately launched, and it appeared that the fault came down to a miscalculation made on the drawing board. As bridge engineer Kevin Lowther explains.
Here we've got the original design drawings for the bridge, and we can see here on the drawing that it shows a 3/8 thickness of plate, which should have been 3/4, which would have made all the difference.
It might not sound like a lot, but this was crucial to the integrity of the entire structure.
It's a big, big difference from that to that, twice the thickness. And as an engineer, you look at something which is 3/8 of an inch thick and think that isn't very strong, not particularly when it's got to support all of the load that it's got.
Although the difference in width for a structure of this size might seem tiny, we're only talking about 3/8 of an inch or 9 millimeters. It actually made all the difference, and the consequences, as we now know, were catastrophic.
Here we are. This is where the buckling of the bridge happened. Here's the diaphragm, and we can see here that it's 19 mil or 3/4 of an inch thick. This is what the original design asked for.
This seemingly tiny error meant the structure didn't have enough strength to support itself before it was fixed in place, and the whole thing came crashing down.
As the 75-meter span was lowered into place above the town, the diaphragm that was meant to keep it stable simply didn't have the strength to handle the load, causing the support to buckle and collapse.
The further the span stretches out unsupported, the more strength it needs, and this proved to be the fatal flaw in its design.
You know, this tremendous construction, I think it's 5,000 tons altogether going across there. And eventually they found, of course, that on where it bent over Pier 6, there was insufficient strengthening.
One final piece across the river, it was sticking out, it was cantilevered from this final pier. The weight of the bridge wanted to pull this end of the bridge down. And if this support isn't strong enough, this is exactly what happened. The whole thing bent around this pier point here, with the diaphragm inside failing catastrophically.
In 1972, after the 2-year investigation was completed, work restarted, with the Clevi Bridge finally opening on March the 20th, 1975.
In its first year, nearly 900,000 vehicles used the bridge, and today around 4 million cross it every year. The old ferry would need to make 400 crossings a day just to keep up.
As a result of the disaster, new regulations were established for both the design and construction of all box girder bridges in the UK.
If there is a silver lining as a result of this disaster, new and much more rigid standards were brought in. So hopefully a tragedy like the Clevi will never be repeated.
Nearly 50 years later, the Clevi Bridge catastrophe remains the last major bridge disaster in the United Kingdom.
This bridge was a much-needed and vital connection to bring these two parts of the country together. This time, it looks like engineers have got it right.
Thankfully, for the last 49 years, it's been as safe as houses.
With big engineering, disaster can strike while the paint is wet and the welds are still warm. But sometimes problems can lie hidden until Mother Nature intervenes. Like this iconic crossing in Wisconsin.
This structure came dangerously close to a catastrophic failure.
The flaw in this bridge almost caused a tragedy.
The bridge was clearly cracking and buckling.
The fear was that the entire structure might come tumbling down.
The city of Milwaukee takes its name from an indigenous American word meaning good, beautiful, and pleasant land. Structural engineering professor Chris Rubble is a local.
One of the great things about Milwaukee is that we have all 4 seasons. We have spring, summer, fall, and winter. Falls are fantastic, beautiful leaves. We have great resources like Lake Michigan.
Over the years, this stunning city has invested in its growth, particularly by developing its infrastructure. One project that was a source of pride was the construction of a bridge over the Milwaukee River, named after one of the city's longest-serving mayors. The Daniel Hohen Memorial Bridge opened in 1977 and has become a key element of a larger transportation system. Local journalist Jim Nelson explains.
The Hohen was part of a system of road projects that created a network of freeways around Milwaukee County.
The Hohen Bridge has become an iconic part of the city's skyline, and that is down to its streamlined design.
It's a bridge of 3 sections. At either side, there is an approach section with what is known as a tied arch bridge at the center.
So the Hohen Bridge is actually 3 bridges in one. It has south approach and north approach, which are just girder span beams, but then the main span that goes over the water is actually a tied arch bridge. So this is an example of a tied arch bridge. The arch, if we didn't have the bottom ties, which are the rubber bands at the bottom, it would want to thrust horizontally at the base of this arch. But because I've put these rubber bands in there to hold it in place, that takes the tension and the thrust that wants to go laterally such that it can just sit on my hands. And that's, in essence, what's happening with the middle span of the bridge.
In a tied arch bridge, the arch supports the deck, and the deck stops the arch from pushing outward. The arch and deck balance each other, which reduces the need for supporting abutments, making these bridges easier to build. Engineering professor Farhad Ansari explains the advantages of this design.
So imagine this could be the same analogy like a bow and arrow, where you have a bow and your arrow is applying the force, and it actually transmits all the forces within the structure itself. It doesn't let any forces coming externally. So by having a tied arch, we are increasing the force carrying capacity. We don't need a large abutment. We can prefabricate the arch and bring it by barges and just basically put it in place.
The Hohen Bridge carried traffic safely for decades, until a hidden engineering flaw came to light in a big way. On December the 13th, 2000, a commuter using the Hohen Bridge witnessed something alarming.
A motorist who was driving over the northbound section noticed that something wasn't quite right and called 911.
Drivers noticed that an important segment of the bridge unexpectedly started sagging, and pieces of debris and chunks of concrete and so forth from the bridge fell on Jones Island, and the fear was that the entire structure had been compromised and might come tumbling down.
The bridge was clearly cracking and buckling, and the bridge deck was sagging down by around 4 feet, or over a meter.
This happened in the morning time during the rush time. No one was hurt, but the bridge was immediately shut down due to safety concerns, obviously, and the bridge remained closed for quite a bit of time so they could inspect the bridge and find out what the reason for the collapse was.
It's kind of fortuitous that the portion that failed did so in a relatively limited way, and they caught it in time, because if they hadn't, I mean, many of us who travel the bridge frequently can only imagine the kind of catastrophe that that would have caused if any or all of this bridge had failed.
Over the years, the bridge was forced to carry heavier loads.
The past decade's traffic has increased greatly. There's no doubt that over time, growing traffic had an impact on Hohen Bridge. For me, this is the responsibility of engineers to predict and take into account.
The investigation revealed the problem was not the increased load, but something that lay in the bridge's support beam structure. 2 of the 3 steel girders supporting one section of the southern approach span exhibited a series of full-depth fractures.
The actual failures occurred at the connections of these K-bracings, where we had a through-the-depth crack in these 3 sections, another one right here, and this connection in the middle, and the last one was not as severe, and the cracks didn't go through the whole depth of the web. And actually, because we had sufficient redundancy, if this girder also at this connection had a through-the-depth crack, the whole section would have failed. However, this redundancy helped the structure. The structure failed, but it didn't collapse.
Analysis of the cracked steel under an electron microscope identified the failure as a brittle fracture.
Brittle fracture is often caused by low temperatures. If the steel temperature is at or below its brittle to ductile transition temperature, then it will be susceptible to brittle fracture.
The ductile to brittle transition temperature is the point at which the strength of a material is significantly altered and often compromised by the surrounding air temperature. For steel, this occurs around 0 degrees centigrade, so when the temperature falls below freezing, which is common in Milwaukee's winter, steel can become brittle.
There's no doubt that stresses from extreme weather contributed to the failure.
But while Mother Nature played a part, it wasn't the only factor. On closer inspection, engineers noticed the cracking had originated from the joints of the bridge's lateral bracing. These connections were deemed too close together and too rigid, leading to a reduction in the bridge's overall fracture resistance. Elements of the bridge that had been installed to give it strength had actually made it weaker. Reopening the crossing would take some major engineering.
The fix was that they demolished, through controlled demolition, several segments of the bridge, brought it down and rebuilt them with a less constraining cross-bracing detail that we see in the bridge on the southbound area today.
The failed section of the bridge had to be completely removed, and a thorough inspection of the remaining parts was conducted.
They did find that they didn't need as much bracing as was put in the original details, so they were able to remove quite a bit of the bracing in the bridge.
The Hohen Bridge is now a lot more flexible and a lot safer. Crucially, it's also better suited to the elements, but this came with a hefty price tag.
The repair budget for this fail was more than $12.4 million.
Despite the high price tag, important lessons were learned.
We were able to change some of the bridge codes such that we could introduce details, especially for the cross bracing, that are not constraining and can work better in this sort of an environment with a steel bridge, so that we don't have this sort of brittle failure with the cracking propagating through the bridge girder all at once.
Understanding failures in engineering projects could ultimately save time, money, and lives by changing design philosophies and helping engineers understand the situations when mistakes and errors can be very costly.
The age-old battle between engineers and Mother Nature isn't always a fair fight. Even though a structure seems indestructible, a simple fail can have catastrophic consequences. Like this Spanish dam that was pushed to its breaking point.
This was a brutal clash between engineering and Mother Nature.
Estamos justo sobre el río Júcar, sobre el devastador.
An engineering disaster with a lasting legacy.
The first Tous dam only managed to stand up to this region's turbulent weather for 4 years before disaster struck.
The picturesque province of Valencia lies on the southeast coast of sunny Spain.
Spain's Mediterranean coast is known for long, very dry periods, punctuated by brief spells of heavy or torrential rain.
Local journalist Isabel Domingo knows the weather in this region well.
En esta zona, en la comarca de la Ribera y también en la comarca de la Safor, uno de los principales problemas es que cuando llueve, llueve mal, que es la expresión o no sabe llover, que es lo que solemos decir aquí. ¿Por qué? Porque cae una gran cantidad de agua en muy poco tiempo.
All that rain ends up in the Ucar River. It flows from its source more than 1.5 kilometers up in the mountains. And although it may appear tranquil today, heavy rainfall can result in a raging torrent.
With high elevations, water only wants to go in one direction and fast, down.
The engineering solution to this problem? The mighty Tous dam.
Conocido como el devastador, y que obligó a construir esa presa de Tous para 3 funciones: evitar las riadas, como la de 1982, generar un canal para todo el regadío de la zona y luego también para el consumo humano, porque esta presa de Tous también abastece tanto a la comarca de la Ribera como al área metropolitana de Valencia.
Standing more than 90 meters high, this concrete gravity dam is built to cope with anything the unpredictable region throws at it. José María Benlliure is in charge of dam operations.
La función de la presa es fundamentalmente la laminación de las avenidas. El río Júcar es un río Mediterráneo que puede multiplicar sus caudales por 1000 en las épocas de las grandes avenidas. La función, por lo tanto, fundamental es evitar las inundaciones de las poblaciones y del territorio que hay aguas abajo de esta presa.
The Tous Dam is an epic piece of engineering designed to protect hundreds of thousands of people from dangerous flooding brought on by torrential rains. So whatever happened behind the dam, by regulating the output, the people living downstream should stay safe.
The Tous Dam is the perfect fit for Valencia's unpredictable climate. But this isn't the first dam to stand here. Its predecessor, built in 1978, hid a major engineering fail that was dramatically revealed soon after construction.
The first Tous Dam only managed to stand up to this region's turbulent weather for 4 years before disaster struck.
On October the 20th, 1982, a freak rainstorm hit southern Spain.
In just 24 hours, the region experienced 22 inches or almost 56 centimeters of rain around here. That's the average for an entire year. Water levels rose behind the dam and started to reach dangerous levels.
When the first operator reported for work the next day, water was already approaching the crest of the dam.
Water spilling over the top of the dam or overtopping is one of the worst things that can happen. So nearly all dams have safety release valves called spillways. By opening gates at the top, water can be released in a controlled way.
The dam operator attempted to open the spillways to lower the water level, but they were stuck in place and wouldn't budge.
With the gates stuck shut, the water level continued to rise. And by early evening, water gushed over the crest.
Suddenly, the Tous Dam collapsed. A raging torrent headed downstream, leaving a path of destruction in its wake. An emergency evacuation was called for the 100,000 people living in surrounding towns.
Aquí en Gavarda la Vieja apenas quedan 4 casas, la iglesia. Esta es la vieja iglesia de Gavarda la Vieja. Aquí hay una placa que recuerda aquel hecho fatídico del 20 de octubre de 1982, una placa que nos marca hasta dónde llegó el agua, unos 6-7 metros.
Across the region, tragically, more than 20 people lost their lives. Survivors were left asking, what exactly had gone wrong? After the drastic floods, the Tous Dam lay in waste. Experts immediately began to investigate how this disaster had spiraled out of control. One obvious flaw was in how the spillway gates were operated.
The problem was that the storm knocked out the power, but the spillway gates, the emergency release valve, needed power to open.
There was an emergency generator, but it was located near the base of the dam.
The emergency generator had been swallowed by the flood early that morning, and by the time a replacement made it through the floods, it was too late to do any good.
And yet, the power source alone wasn't to blame for this disaster.
Even if they had opened, an investigation concluded that the spillways had too low a capacity to cope, so the overtopping may still have occurred.
Engineer Don Vicente Fulana, who managed the rebuilding of the dam, explains.
Y al resbalar por el faldón de agua abajo del azud, se lleva las piedras, porque al ser el azud construido con materiales sueltos, no tiene coherencia y por lo tanto se lleva la presa poco a poco.
Once the water breached the dam, disaster was inevitable downstream, as Professor Ignacio Escuder demonstrates.
So what it's useful to see here is how the water behaves. Now we see a very calm water here, but what's going to happen here is going to help you to understand the power of water in order to create destruction. So just have a look to this. Carlos, adelante.
The water pressure is increased to demonstrate what happened as the dam began to overtop.
Let's say we are now at the toe of the dam, and the energy has to be compensated. And it's going to be a very turbulent area, and it's going to be an increase in water level, and the energy for erosion and destruction is going to look like this.
Increasing the water pressure further reveals what happened downstream when the dam had failed completely.
Still, we would see something like this in the river, going downstream the valley. Very high velocities, the need of energy dissipation, high water levels, and all this energy available for erosion and destruction downstream.
With the Tous dam well beyond repair, future flooding was a constant threat to the region. The only option was to build a new dam.
Para eso, yo exigí que se dotara a la presa de la capacidad de resistir un caudal que fuera el máximo probable en aquel punto.
The new and improved dam was finally completed in 1996, more than 10 years after the disaster. Today, the Tous dam is safer than ever, making flooding in this region a thing of the past.
El volumen de agua retenido por la presa de Tous moderna es del 20% de esa cifra. De tal manera que el 80% de su capacidad queda esperando una avenida.
Although the area is now safe from flooding, the Tous dam disaster still resonates with engineers worldwide.
If there is any redemption in this disaster, it is the fact that the Tous dam failure has improved dam safety procedures and construction techniques.